Today we will start the final unit in this course. It's Unit 4, which will be on instantaneous power, average power, reactive power, complex power, and maximum power transfer. Lecture 9-1 deals with instantaneous, average, and reactive power. This reading is from sections 8.1 and 8.2 in the text. At the conclusion of today's lecture, a student should be able to briefly and clearly explain instantaneous power, average and reactive power, leading and lagging power factor. In addition, a student should be able to calculate the instantaneous, average, or reactive power for a circuit, given the waveform, voltage, and/or current. Finally, the student should be able to determine whether a power factor for a load is leading or lagging by calculating the voltage and current characteristics. Recall that from our study of DC circuits, power is equal to V times I, and the units are watts. This is referred to as the instantaneous power. When the voltage and current are sinusoidal expressions instead of constants, this relationship is a lot more complicated. P of t would be V times I, so that would be V sub m cosine omega t plus theta V minus theta I times I sub m cosine omega t. Using algebra and trig properties, we can rewrite this as P of t is equal to 1/2 V sub m I sub m cosine theta V minus theta I plus cosine theta V minus theta I cosine 2 omega t minus sine theta V minus theta I sine 2 omega t. If we created a graph of this instantaneous power expression, what you would see is that it has twice the frequency of the voltage and the current, and also that it does not have an average value of 0. In other words, there's a DC offset. That DC offset is 1/2 V sub m I sub m cosine theta V minus theta I. The other thing you should notice is that the amplitude of the sinusoid is 1/2 V sub m I sub m. The power may be negative for a portion of each cycle, which implies that the energy stored in an inductor or capacitor is being released, or it may be positive when the energy is being stored. So a simpler way, and what we would typically use in class for writing the instantaneous power, is P of t is equal to P plus P cosine 2 omega t minus Q sine 2 omega t, where P is the average or real power, and it's 1/2 V sub m I sub m cosine theta V minus theta I. The units are watts. This average power describes the power in a circuit that is transformed from electric to non-electric energy. Examples of devices that convert electric energy to thermal energy are stoves, ovens, toasters, irons, water heaters, electric clothes dryers, or hair dryers. Reactive power has the symbol of Q, and it has units of volt ampere reactive, and Q is equal to 1/2 Vm sine of theta V minus theta I. Reactive power is associated with the energy stored in an inductor or capacitor. This is the energy that is exchanged back and forth between the source and the load, and it is not converted into non-electric energy. The following table summarizes some key concepts about average and reactive and instantaneous power. So if you notice here, we have a very simple circuit, one that's purely resistive, a voltage source and a resistor, one that's purely inductive, a voltage source and inductor, and one that's purely capacitive, a voltage source and capacitor. So recall from prior lectures that when you have a resistor, the voltage and the current are in phase, and the average power is equal to 10 if we assume that we have a current of 1 amp and a resistance of 5 amps. And notice all of these graphs have been made assuming a resistance of 5, and so we would have an average power of 10 watts, and the green line represents the instantaneous power. So when you have a resistor, it has an average power greater than 0, and it has a reactive power Q equals 0. And notice that the phasor diagram to show the relationship between the voltage and current has been copied here from prior lectures to help. For the inductor, V of T and L, what you'll notice here is that an inductor has an average power of 0, and that the instantaneous power has double the frequency again, but it is symmetric about the time axis. Same for the capacitor. Notice that the voltage lags the current by 90 degrees for the capacitor, and it also has an average power of 0 and double the frequency of the voltage and the current. So the average power for inductors and capacitors is 0, and the reactive power is greater than 0 for an inductor, and the reactive power is less than 0 for a capacitor. And the voltage and current phasor diagrams have been drawn here to help with the leading and lagging for the current and the voltage. So P of T for a resistor is P plus P cosine to omega T, where that average power P is the DC offset of the sinusoid. For an inductor, P of T is equal to negative Q sine to omega T. So what you should see here is that that is always going to be symmetric about the time axis. And P of T is the same for a capacitor. It's negative Q sine of 2 omega T. Okay, let's try an example. For the following circuit, what is most approximately the average power dissipated in the load? The easiest way to do this problem is to actually combine these impedances to redraw this as a voltage source, 115 with an angle of 40 degrees, and the units are volts, and parallel with an impedance ZEQ. ZEQ is 1 plus J2 plus 5 plus J, in parallel with 2 plus J6, and parallel with negative J8. So ZEQ is equal to 4.86 plus J3 ohms. So the current I from the source would be equal to 115 with an angle of 40 degrees divided by 4.86 plus J3, which is 20.14 with an angle of 8.3 degrees, and the units are amps. So using our average power formula, we now know the voltage and the current. We can solve. P is equal to 1/2 the voltage magnitude times the current magnitude times the cosine of theta V minus theta I, which is equal to 1/2 times 115 times 20.14 times the cosine of 40 degrees minus 8.3 degrees, which equals 985 watts. So most nearly the answer would be letter B. So just like we could confirm that a DC circuit obeyed the law of conservation of energy, we can also confirm that an AC circuit obeys the law of conservation of energy. The difference is now we don't just look at average power, but we also have to look at the reactive power. So we're going to find the average and reactive power for each of the elements in this circuit and show that it does indeed obey the law of conservation of energy. First thing we're going to do is we're going to use the node voltage method, or KCL, to solve for the voltage at this node, which we will call VC for the voltage across the capacitor. So we'll have VC minus 50 over 20 plus VC over negative J10 plus VC over 10 plus J5, and that equals 0. So the voltage across the capacitor is 17.46 with an angle of negative 24.78 degrees. So if I want the current through the capacitor would be equal to 17.46 with an angle of negative 24.78 degrees divided by negative J10, which yields 1.746 with an angle of positive 65.22 degrees, and the units are amps. So there's only one element that can deliver power, and it's the voltage source. Although inductors and capacitors can release energy back into the circuit, that would be energy that's stored from the voltage source. So we assume the only element that delivers power would be the 50-volt source. So now that I know the voltage across the capacitor, I can find the current from the source, which is also the current through the 20 ohm resistor. IS would be equal to 50 minus VC over 20. So the current from the source is 1.746 with an angle of 12 degrees, and the units are amps. So now if I want to find the current through the 10 ohm and the J5 ohm impedances, I'll call that IL. IL would be equal to VC over 10 plus J5. So IL is equal to 1.56 with an angle of negative 51.34 degrees, and the units are amps. And now that I know IL, I can find the voltage across the 10 ohm resistor, which is 10 times IL, or 15.62 with an angle of negative 51.34 degrees, and the units are amps. And I can find the voltage across the J5 inductor, which is J5 times IL, which is 7.81 with an angle of 38.66 degrees, and the units are volts for both of those. So now we can put these values on our table. 50 with an angle of 0 degrees for the source, 34.92 with an angle of 12 degrees for the 20 ohm resistor, 15.62 with an angle of negative 51.34 degrees for the 10 ohm resistor, 17.46 with an angle of negative 24.78 degrees for the negative J10 ohm capacitor, and 7.8 with an angle of 38.66 degrees for the J5 inductor. Now let's do the currents. The 50-volt source and the 20 ohm resistor are in series, so they have the same current, and it's 1.746 with an angle of 12 degrees. The 10 ohm resistor has a current of 1.56 with an angle of negative 51.34 degrees. And the negative J10 ohm capacitor has a current of 1.746 with an angle of 65.22 degrees. And finally, the J5 ohm inductor has the same current as the 10 ohm resistor, which is 1.56 with an angle of negative 51.34 degrees. So to find the average power for the voltage source, it's P. It's going to get a negative sign because it's delivering power. So it's going to be negative Vm Im cosine theta V minus theta I, which would be 50 times 1.746 times the cosine of 0 minus 12 degrees, which equals negative 42.696 watts. Q for the 50-volt source would be negative Vm Im times the sine of theta V minus theta I, which is 50 times 1.746 sine of 0 degrees minus 12 degrees, which is positive 9.075 watts. And we'll put that on the table. 9.075 watts. So now recall, resistors have a Q value of 0. Capacitors and inductors have a P value of 0. So we only need to find one or the other. So for the 20 ohm resistors, I can go ahead and put Q is 0. And for the inductor and capacitor, I can go ahead and put P as 0. So now for the 20 ohm resistor, the power would be 34.92 times 1.746 times the cosine of 0 degrees. So for the 20 ohm resistor, it's 30.485 watts. We would do similarly for the 10 ohm resistor to get 12.184 watts. So Q for the capacitor, negative J10, would be 17.46 times 1.746 times the sine of negative 90 degrees. So for that capacitor, that would be negative 15.278 var. And similarly for the J5 inductor, it would be 6.092 var. So if we sum these columns, what we should see here is that the power sums to 0 and the reactive power sums to 0. So this circuit does obey the law of conservation of energy. Note that the angle theta V minus theta I comes up frequently in our power calculations. This angle is referred to as the power factor angle. The cosine of the power factor angle is called the power factor, and it basically describes how efficiently a source delivers power to a load. So the power factor is equal to the cosine of theta V minus theta I. The sine of the power factor angle is called the reactive factor, RF, and it's the sine of theta V minus theta I. We very rarely use the reactive factor in class, but we use the power factor often. Based upon these relationships, we can rewrite the average power as P is equal to 1/2 V sub m I sub m PF, and we can write the reactive power as Q is equal to 1/2 V sub m I sub m RF. So thinking about the table on the prior page with the purely resistive, purely inductive, and purely capacitive circuits, we have now the power factor relationship. If it's a purely resistive circuit, the power factor is equal to 1 because theta V minus theta I is equal to 0 degrees. If it's an inductive circuit, the power factor is greater than 0. The power factor angle is greater than 0, and the power factor is equal to 0. If it's a purely capacitive circuit, then the power factor angle is less than 0, and the power factor is equal to 0. Another handy tool that we use for power factor calculations is called the power triangle. The power triangle can be related to the impedance, which we will talk about today. So the impedance is Z is equal to V over I, where that can be written in angle notation as the magnitude of Z with an angle of theta V minus theta I. Therefore, R plus JX. So what you'll see here is that the angle between R and X is actually the power factor angle. So the cosine of that angle is the power factor, where the hypotenuse of the right angle triangle is the magnitude of Z. The real part is the horizontal axis resistance, and the imaginary part of the reactance is the vertical part. So now let's use this concept to determine whether the load shown here has a power factor, what's the numeric value, and whether it's leading or lagging. The first thing we want to do is to find the equivalent impedance between terminals A and B. So ZAB would be equal to 4 plus J in parallel with J2, that entire quantity minus J and all of that in parallel with 1. So that equals 0.445 plus J, 0.176 ohms, or in angle notation, 0.479 with an angle of 21.5 degrees, and the units are ohms. So 21.5 degrees is the power factor angle. So the power factor is the cosine of 21.5 degrees, which is 0.93. Power factor has no meaning if you don't put lagging or leading on it. You always must put lagging or leading. How do you know which one to select? If the power factor angle is greater than 0, as it is in this case, if 21.5 degrees is greater than 0 degrees, then we say that the power factor is lagging. Let's try another example. For the following circuit, find the power factor for the voltage source. Similar to the one above, it's probably simpler to find the impedance for the load. So we'll have the voltage source 50 with an angle of 0 degrees, and units are volts. And we want to find the equivalent impedance at the load, which we will call ZEQ. ZEQ is equal to 10 plus J5 in parallel with negative J10. The result of that quantity, we add 20. So the impedance is 28 minus J6 ohms, or in angle notation, 28.64 with an angle of negative 12 degrees. We'll put that here, 28.64 with an angle of negative 12 degrees. So the power factor angle is negative 12 degrees. So the power factor is the cosine of negative 12 degrees, which is equal to 0.978. Because negative 12 degrees is less than 0, we would say it's 0.978 leading. This concludes today's lecture on instantaneous power, average power, reactive power, and the power factor.